So far, everything that we've talked about has been a linear model. In order to get a sense for the new kind of model that we're going to introduce in this section, we're going to go back to what we saw in data tables. So in this data table, we're going to see a certain pattern. Each time we go down a row, the input value increases by 1, and the output value, well, let's see, going from 1 to 3, that's an increase of 2. From 3 to 5, that's also an increase of 2. From 5 to 7, an increase of 2. 7 plus 2 is 9. 9 plus 2 is 11. Every time we go down a row in the table, the change in x is plus 1, and the change in y is plus 2. And so we know that this is a linear relationship. Yes, these values are linearly related because the rate of change is constant. And now we can do all of the things we like to do with linear relationships. We can write down the slope. The slope is the change in y over the change in x. So it's 2 over 1 is 2. The intercept is the value of y when x is 0. So the intercept is 1. And so because this table shows us the slope and the intercept, we can directly write down the equation y equals 2x plus 1. This is a linear relationship if we go to a graph and we plot each pair that appears in the table. So when x is 0, y is 1. When x is 1, y is 3. When x is 2, y is 5. When x is 3, y is 7. When x is 4, y is 9. When x is 5, y is 11. This is just all of the pairs that we see in the table. If we go through and plot those points, they all lie along a straight line. So we can draw a straight line that passes through all of those points. So this is a linear relationship. Constant change in x produces a constant change in y. We can write the equation as y equals mx plus b. When we graph it, the points all lie along a straight line. Now, contrast that with the pattern that we're going to see in this next example. In this next example, we see a similar pattern in the inputs. Every time we go down a row, the input increases by 1. But when we go down a row, the outputs are doing something different. So from 1 to 2, that's adding 1. From 2 to 5, that's not adding 1. 2 plus 3 is 5. 5 plus 5 is 10. 10 plus 7 is 17. 17 plus 9 is 26. So we see that when we go down a row, we're adding all different numbers. But there's a pattern to those numbers. The numbers that we're adding themselves go up by 2. In this table, we see that the change in x is constant, but the change in y is not constant. Y changes by a different amount every time we go down a row. but something is constant. What we're seeing here, we'll describe this as the change in y is constant. So it's not just finding the differences in the y values. We have to go an extra step of finding differences, but then we find something constant. So these variables are not linearly related. Why are they not linearly related? Because the rate of change is not constant. Since these variables are not linearly related, we expect that the graph is not going to be a straight line. Just putting a little copy of the table down next to the graph so we can have them on screen at the same time. We see that when x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 5. When x is 3, y is 10. When x is 4, y is 17. There it is. And when x is 5, y is 26. And now we see if we try to draw a straight line through this graph, we can't do it. There's no single straight line that passes through all of these dots. This graph is not a straight line. Now there is a curve that passes through all these points, and we're going to see that in a minute. But right now what we're noticing is that this is not a linear relationship, but there is a clear pattern here. This sort of relationship is what's going to give us what we're going to call quadratic functions.